Hello, welcome to our paper on Unified Framework for Open World Compositional Zero-Shot Learning. In this work, we investigate the task of Open World Compositional Zero-Shot Learning, which addresses the challenge of recognizing novel compositions of known primitives and entities. Each sample consists of two elements, image and corresponding text label with the composition, and it divides into attributes and object label. Testing datasets consist of two subsets, scene pairs, which contains all attribute and object compositions present during training, and unseen pairs, which consists of all attribute and object compositions that were not available during training. Prior works can be categorized into two distinct groups based on the output prediction space, referred to as closed world setting and open world setting. Conventional CZSL methods utilize a closed world setting in which both seen and unseen pairs are present during inference evaluation. Yet the output space only consists of known number of seen and unseen pairs. On the contrary, in open world setting, the output space consists of all possible combinations of attribute and object pairs. Most notable works in compositional learning only facilitate simple fusion within two modalities. We hypothesize that a simple fusion of outputs even from high-performing unimodal embedders may prove inadequate when learning intricate vision language-based compositions. Our proposed model integrates dual modalities within a unified framework, which reduces model overhead while maintaining high performance. Our proposed method is structured around three modules. In order to generate image embeddings, first we divide the image into P by P patches and flatten them into vectors. Then we concatenate three class tokens, accounting for attributes, objects, and pairs. For word embeddings, we create a fixed auxiliary vocabulary input for the dataset by collecting BERT embeddings for each attribute and object. The objective of Top K embedding selection module is to perform visual assisted vocabulary mapping to create a text input for the primary multimodality transformer. First, we must impose cross-attention between image embeddings and word embeddings to produce an attention map. Attention scores for each word is calculated by summing the attention map along the image axis to produce a 1D vector. From sorted attention scores, we select the text embeddings of words which have top K highest attention scores. Text input to the multimodality transformers is created by concatenating top K attributes and objects. In order to separate two modalities, text and image embeddings are combined with their respective modal type learnable embedding vectors, then concatenated along the embedding axis to form input sequences. Contextualized vector is iteratively updated through d number of transformer layers with multi-head self-attention to obtain the final contextualized vector. Given three class tokens, sparse linear compositor computes an attribute prediction vector, an object prediction vector as auxiliary outputs, and a composition vector between all the attributes and objects. Initially, the first two class tokens are processed through two learnable MLP heads. Concurrently, we normalize these MLP head outputs and multiply them to compute the decomposition pair predictions. Composition pair output is calculated by a learnable addition of corresponding attribute and object vectors. Lastly, we combine both the decomposition pair prediction and compositional pair prediction to produce the final pair prediction. This table provides the quantitative outcomes of our methodologies on MIT State dataset across various evaluation matrices including area under the curve, with seen and unseen accuracy and harmonic mean. Our models consistently surpass state-of-the-art methods in all matrices. This table provides the quantitative outcomes of our methodologies across same evaluation matrices with CGQA dataset. Our models consistently surpass state-of-the-art methods in all matrices. This table provides the quantitative outcomes of our methodologies across various evaluation matrices with a new dataset. Even with high number of compositions, our models consistently surpass state-of-the-art methods in all matrices. To evaluate the effectiveness of the proposed model, we conduct experiments against CLIP and CLIP-based CSP. Even though the proposed model struggled in MIT states, it outperformed CLIP-based models with a significant margin in CGQA and VAW CZSL datasets, which showcases the robustness of the model when scaling up the output space. Presenting our qualitative results for each image, 3 columns illustrate top 3 results for attributes, objects, and compositions. In all instances, the majority of the top 3 predictions describe visual content of the images acceptably well. We present a similar structure for CGQA as well. We can observe the effect of an input image containing multiple objects as well as objects comprising multiple attributes. Finally, we present qualitative results for VAW and we notice similar results with previous datasets. Contribution of the proposed method is threefold. We introduce a unified framework for OW-CZSL by utilizing a single transformer while preserving model performance. We propose top K selection module to mitigate the challenge of exhaustively exploring all potential pairings during the inference process. We propose a novel sparse linear layer to facilitate the integration of multiple tokens, aiding in the disentanglement of attributes and objects while enabling the generation of compositions with reduced computational complexity. Thank you for tuning in to our video. For in-depth information, please refer to our full paper.